Historically, deploying software meant buying physical hardware. If an engineering team wanted to launch a new application, they had to provision a dedicated physical server. To run it, one application required one machine. Because applications rarely experience maximum traffic volume at all times, these dedicated servers typically sat idle. On average, physical hardware ran at just 5 to 15% CPU utilization, leaving the vast majority of the server's processing power entirely wasted. Scaling up required ordering new servers, waiting weeks for shipping, manually racking hardware in data centers, and configuring the network. Every new application carried a massive upfront capital cost. Paying for 100% of a server's capacity to only use 10% of it while enduring weeks of provisioning time made strictly physical hardware scaling economically and operationally unviable for modern development. Hardware costs were only half the equation. Software teams also faced a massive bottleneck in deployment caused by environmental drift. Environmental drift occurs when the underlying software configurations differ between the machine where code is written and the server where it ultimately runs. A developer writes an app on Ubuntu 22.04 and Node 18. Local dependencies match. The code executes perfectly, but pushed to the test server, it crashes. The server runs CentOS 7 and Node 14. Version conflicts cause the application to fail entirely. This is the classic developer complaint. It works on my machine. Without a standardized execution environment that remains completely identical from development to production, scaling software teams is impossible due to unpredictable deployment failures. To solve the massive waste of physical server capacity, the industry introduced hardware-level virtualization, commonly known as virtual machines. As illustrated in this architecture diagram, engineers inserted a hypervisor layer directly above the physical hardware. A hypervisor is a specialized software layer that divides a single physical machine's CPU, RAM, and storage into multiple, completely isolated virtual environments. There are two main approaches. Type 1, or bare metal, runs directly on hardware for maximum efficiency in data centers. Type 2, or hosted, runs on an existing OS, adding slight overhead but ideal for local developer laptops. By allowing a single bare metal server to host dozens of independent applications securely, virtual machines pushed resource utilization past 80%, laying the foundational technology for modern cloud computing. Achieving this hardware efficiency required a significant architectural trade-off. Looking at the layered view of a virtual machine, you can see that above the hypervisor, every single isolated application requires its own complete duplicate operating system, labeled here as the guest OS. Packaging an entire operating system inside every VM results in gigabytes of storage bloat per image. Furthermore, because a full OS must boot up from scratch every time an instance starts, provisioning a new VM can take several minutes. Virtual machines successfully optimized hardware usage, but they introduced immense software bloat. Engineering teams needed a lighter abstraction model that could provide isolation without the penalty of a duplicate operating system. The next architectural evolution was the container, a form of OS-level virtualization. Look at the OS row in this head-to-head comparison. While a virtual machine requires a full guest OS, a container strips it out. Containers share the host machine's OS kernel, the core component managing system resources, directly, achieving lightweight, process-level isolation. Removing the operating system reduces the size of a container image from gigabytes down to megabytes, and without a full OS to boot, a container starts executing its application in fractions of a second. Process-level isolation shifts the abstraction boundary from the physical hardware layer up to the application layer. To operationalize Linux containerization for mass development, the industry standardized on the Docker engine. This diagram maps the Docker architecture. A developer interacts with the Docker client, sending commands to the Docker daemon, the background process that builds and runs containers. The daemon manages static, read-only images and active, running containers built from those images. Developers control this lifecycle using a basic CLI workflow. As highlighted here, running Docker run with a -p flag maps support on the host machine to a port inside the container, exposing the application to the network. Docker provides a unified, standardized interface, allowing engineering teams to build, ship, and execute isolated application processes on any machine. Every Docker image begins as a declarative text blueprint known as a Docker file. As shown on the left, the Docker file outlines a rigid set of instructions. It packages the application code alongside the exact runtime, system tools, and libraries required for execution. When the Docker daemon processes this file, each individual instruction, like copying a file or installing a package, creates a discrete, immutable layer stacked together to form the final image. Docker aggressively caches these layers. Because modifying any single layer forces all subsequent layers above it to rebuild, a strategic engineering rule is applied. Frequently changing elements, like the application source code, must be placed at the very bottom of the Docker file. This layered file system architecture ensures that when code changes, only the altered layers are recompiled, making image builds blazing fast and highly portable over a network. By default, containers are completely ephemeral. When a container crashes or is intentionally stopped, any data written to its local file system is permanently destroyed. While this statelessness is a benefit for web servers, it is a catastrophic problem for database applications like PostgreSQL or MongoDB, which require data to persist across restarts. To persist data outside of a container's lifecycle, engineers use Docker volumes. Volumes bridge temporary compute and permanent storage. A bind mount maps a specific directory on the host machine directly into the container, making it useful for local development. For production databases, teams use named volumes, persistent storage spaces managed entirely by Docker itself. Managing state via volumes provides the critical architectural bridge, allowing ephemeral compute instances to safely interact with permanent data storage without risk of data loss. With the compute layer isolated and the storage layer decoupled, teams can execute the ultimate operational workflow of containerized architecture, the push and pull model. The lifecycle begins when a developer builds an image locally. Once verified, they use the Docker push command to upload that exact artifact to a centralized storage hub. This hub is known as a container registry. Teams use public registries like Docker Hub for open source images, or private, secured registries like AWS ECR for enterprise applications. Finally, the production server executes a Docker pull command to download that identical, immutable image and execute it. Because the production server pulls the exact same artifact compiled by the developer, this workflow guarantees absolute environmental parity. The "it works on my machine" problem is permanently solved. Modern enterprise applications are rarely just a single container. They require web servers, background workers, and databases all operating in tandem. To orchestrate these multi-container systems, engineers use Docker Compose. Compose allows teams to define all interconnected services within a single YAML file. A single compose command automatically reads this file, handles the complex networking, maps the shared volumes, and boots the entire application stack in the correct dependency order. Containerization, centralized registries, and multi-service orchestration deliver predictability to software deployments. By standardizing exactly how code is packaged and executed, this stack forms the absolute bedrock required to build automated continuous integration and continuous deployment pipelines.